Imagine for a second, right, that you are staring down at a massive, just an impossibly tangled knot of cables.
Oh, yeah. We have all been there. It is a nightmare.
Right. Just a chaotic, interconnected mess of wires. And, your first instinct might be to just grab the whole thing and pull.
Like trying to force it apart by sheer strength alone.
Exactly. But of course, you've probably done that before, and it really only makes the knot tighter.
Yeah, that never works.
No, it doesn't. The real trick, the elegant solution, is to stop looking at the terrifying hole. Instead, you find one single specific loop.
Right, you isolate the problem.
You shift your perspective.
Yeah.
You pull that one specific piece of string, and suddenly the entire chaotic structure just unravels into a perfectly straight line. Welcome back to the Deep Dive.
It is great to be here.
Today, we are taking a set of highly technical engineering notes, specifically Day 20 on integration by substitution. And we are going to show you exactly how to find that one perfect string to pull.
Which is such a great analogy to start with, honestly, because when we talk about high-level math, people often, they brace themselves for a wall of incomprehensible symbols.
Oh, for sure. It sounds completely overwhelming.
Yeah, but the underlying logic of substitution isn't really about memorizing symbols on a chalkboard. It is fundamentally about untangling complexity.
Well, okay, let's unpack this, because I know the word calculus alone carry this heavy, almost academic weight.
It definitely scares people off.
It sounds intimidating. But the journey we are going on today, it reveals calculus as an elegant shortcut. We are going to trace a single mathematical thread that scales up in complexity.
And we are really going to see it everywhere.
Yeah, we'll start with the sheer physical force of a rocket pushing through the atmosphere, scale down to the invisible flow of electricity in a circuit, and eventually arrive at the abstract architecture of artificial intelligence. And it all hinges on one maneuver.
But, before we can fly that rocket or train a neural network, we really need to understand the mechanics of the maneuver itself.
Right. We have to look under the hood.
Exactly. We have to decode the core magic trick of changing a variable.
Right. So in the engineering notes for Day 20, the foundational problem is presented as like a nested Russian doll of a calculus equation.
That is a very good way to picture it.
I won't read out the raw notation because honestly, it just sounds like a cryptographic puzzle. But picture a complex function completely trapped inside another function.
Right.
And all of that is being multiplied by a rate of change. When you look at it in its raw native state, it seems completely impenetrable.
Impenetrable is definitely the right word.
Yeah.
If you try to attack that nested function head on, if you just pull on the whole knot of cables, you get nowhere.
It just tightens up.
Exactly. The brilliant workaround is that you simply transform the independent variable. What's fascinating here is that the entire structural logic of this trick relies purely on reversing the chain rule of differentiation.
Okay, let's break that down because reversing the chain rule sounds a bit abstract. The process basically follows 4 steps, right? Step 1, you look at that messy, trapped inner function, and you just give it a new simple name.
Right, you just rename it.
You assign it a single letter, usually U. You're essentially like putting a mask over the chaos.
You are isolating the internal mechanism, yes. But step 2 is really where most people get tripped up.
Oh, how so?
Well, you can't just slap a new label on the function and call it a day. You have to differentiate that new substitution.
Right, the math has to balance.
Because if you change the variable you are measuring, you inherently have to change the rate at which you are measuring it. Think of it like a currency exchange.
Okay, I like that.
If you suddenly decide to measure your wealth in euros instead of dollars, you can't just keep your original salary number. You have to apply the exchange rate.
Right, obviously.
So in calculus, that exchange rate is the differential.
Ah, okay. So you are taking the derivative of your new mask, your OJU, to find out how it specifically relates to the original messy variables.
Precisely. You find the mathematical bridge between the old world and the new world.
Which brings us to step 3, where the actual magic happens, I think.
Yes, it is.
Because of that specific mathematical bridge, that terrifying nested equation just collapses.
It does.
The outer layers just fall away, and it reduces down to a clean, brilliantly simple integral, just the letter U.
Yeah, the complexity hasn't been destroyed, mind you. It has just been temporarily contained.
Right, boxed up for a minute.
Exactly, and that sets up the 4th and final step. Because you now have this incredibly simple expression, you can run it right past standard integration tables.
You just solve the easy version.
Yes. And once you have the analytical answer, you just swap your original messy function back in for us.
You know, it really feels like a mathematical Trojan horse.
Oh, that is an interesting way to put it.
Yeah. You take this massive, complicated problem, and you hide it inside a very simple, unassuming wooden horse, which is that letter U.
I see where you're going with this.
You sneak it right past the heavily guarded integration tables, solve it with absolutely no resistance, and then once you're safely on the other side, the soldiers jump out. You take the mask off and reveal the true solved function.
It is actually a surprisingly accurate visual. And the reason the Trojan horse works mathematically is the chain rule.
Right?
In calculus, the chain rule is how we take the derivative of systems within systems. Substitution is simply running that exact film in reverse.
So it's just playing it backward.
It is taking the shattered pieces that the chain rule produced and neatly repackaging them back into their original unified state.
Okay, so we have our Trojan horse. We have the theory of how to hide a complex problem inside a simple variable.
Yeah.
But as we promised, this doesn't just live in a textbook.
No, absolutely not.
It dictates physical reality. So let's look at the first scale of complexity, which is macro forces. Let's talk about aerospace engineering.
This is a perfect place to start because in aerospace, the structural logic of substitution becomes a literal physical necessity.
Wow, a necessity.
Yeah, when you are modeling orbital mechanics or aerodynamic drag, you are dealing with forces that are highly dynamic.
Right, the notes highlight a specific scenario here. A rocket dealing with velocity-dependent acceleration. Basically, the drag force working against the rocket increases exponentially the faster the rocket goes.
Right. It is a nonlinear differential equation of motion.
Which makes sense intuitively, right?
Yeah.
Like, if you put your hand out the window of a car moving at 20 miles an hour, you feel a little breeze.
Sure.
If you do it at 70 miles an hour, your arm physically gets pushed back.
Right. The force scales up.
The force changes based on the speed itself. But wait, hold on. If we know the formula for how drag works, why can't we just integrate the rocket's acceleration directly?
I mean, it seems like you should be able to, right?
Yeah. Just plug the numbers in and solve for where the rocket will be. Since aerodynamic drag changes as the speed of the rocket changes, it's essentially a moving target. Is variable substitution the only way to lock down these changing variables to find position or time?
It is the only way, yes, because it's a moving target, like you said. If you look at the structure of a differential equation, you have velocity, time, and acceleration all twisted together in the exact same mathematical breath.
They're all knotted up.
Right. The rate at which the velocity is changing depends entirely on what the velocity currently is. They are inextricably married. You cannot just integrate that straightforwardly.
So pulling on the whole knot just tightens it.
Exactly. Integrating these nonlinear differential equations of motion requires variable substitution to manually separate the velocity terms from the time terms.
Oh, I get it.
You have to use your Trojan horse, your u-Substitution, to essentially act as a divorce lawyer for the variables.
A divorce lawyer. That is great.
You pull all the velocity components to one side of the equation and all the time components to the other. Only by transforming those variables can you untangle the moving target and create a solvable equation that tells you exactly where that rocket is going to be in physical space.
That is just fascinating. You use the u-Substitution to temporarily freeze the shifting reality of the atmosphere, you do the math, and then you unmask it to get your actual flight path.
Precisely.
All right, so that's physical space, that's macro. Let's scale down now. Let's look at micro forces like invisible energy pushing through circuits.
The domain of electronics.
Yes.
The notes bring us to the design of alternating current, or AC, signal processing filters. Engineers designing these systems have to calculate critical parameters like power dissipation and root mean square voltage.
Right, because unlike a simple battery that just, pushes a steady flat stream of power, alternating current oscillates. It's a wave.
Yes, it is constantly changing direction.
And here's where it gets really interesting. The notes present a problem involving nested frequencies. You have a sine wave and a cosine wave overlapping in the same equation, representing different shifting aspects of the electrical signal over time.
It is a highly complex periodic waveform. You aren't just dealing with a simple up and down current. You have clashing forces.
Right, it's like taking two entirely different complex audio frequencies. Imagine two dense, layered songs.
Okay, yeah.
And you were playing them over the exact same speaker at the exact same time. The sound waves are clashing, they're amplifying and canceling each other out.
It would be a mess.
A total mess. Trying to look at that massive tangled audio file and manually measure the exact amount of pure energy it contains just seems impossible. How does substitution actually fix that?
Well, if we connect this to the bigger picture, substitution isn't just a helpful trick here. It is strictly mandated.
Mandated. Wow.
Yeah, you cannot calculate the power dissipation of that circuit by looking at the raw colliding sine and cosine waves. But think about the relationship between those two waves. What happens if you take your Trojan horse and you say, let equal the sine wave?
Okay. If you use the sine wave,
Okay.
step 2 is we have to find the differential. We
Right.
have to take the derivative of sine, and the derivative of sine is cosine.
Oh, I see.
There it is. Because the derivative of the sine wave is the cosine wave, the exchange rate we talked about earlier perfectly accounts for that second clashing song.
Exactly.
When you swap in your u, the math naturally swallows up the cosine wave entirely. It just vanishes into the differential.
It cancels out perfectly. By substituting the sine wave, you collapse those two clashing signals into a single measurable metric.
That is so elegant.
It really is. The math recognizes that the two waves are just different expressions of the same underlying rate of change. It is the only mathematical pathway to strip away the noise and find the true energy transfer happening in that circuit over a given cycle.
Wow. Okay, so we untangled the rocket's drag from its speed, and now we've used the exact same philosophy to untangle clashing electrical waves to find pure power.
That is two major domains down.
We've conquered the physical and the electrical. Now let's look at the third scale of complexity, digital intelligence. We are taking this exact same math and applying it to statistical machine learning.
This is perhaps the most hidden yet pervasive application of the concept today. Yeah. In the realm of computing and statistical machine learning, algorithms are trying to make sense of massive chaotic data sets. And to do that, they often rely on probability density functions.
Wait, before we start normalizing things, I want to make sure I don't lose the thread here.
Fair enough.
We went from the aerodynamics of rockets and the flow of electricity to, well, data. What exactly are we defining as a density function in this context? How does calculus apply to a spreadsheet of data?
It's a crucial question. Imagine you are trying to train an AI model to predict housing prices across an entire country, or maybe analyze pixel variations in millions of medical images.
Okay, so just an unbelievable amount of information.
Right. You are dealing with an infinite, continuous space of possibilities. A probability density function, specifically the Gaussian distribution, or what most people call the bell curve, is the mathematical shape of that infinite data.
Ah, the bell curve.
Exactly. It shows you where the data clusters and where it fades away. But integrating that bell curve over continuous space is exponentially complex.
Because the raw data is completely chaotic, right?
Right.
Like you're looking at data with wildly different scales.
Yeah.
Maybe one variable in your housing data set is measured in hundreds of thousands of dollars, and another is measured in square footage, and another is measured in decades of age.
Exactly. The algorithm is trying to process a landscape where the mountains are measured in miles and the valleys are measured in millimeters.
That would totally break it.
It cannot inherently compare them. To integrate that bell curve, the raw distribution has to be mathematically transformed.
And the notes give us the specific substitution used for this. It's called a z-substitution. You take the raw data point, subtract the average, and divide it by the standard deviation.
That is the transformation. It is the exact same conceptual Trojan horse we used for the rocket in the circuit, just wearing a different disguise.
So when we train a machine learning model, it's trying to make sense of infinite continuous space. Is this z-substitution essentially a way of like standardizing the currency so the algorithm can actually process the raw distribution? If the AI is overwhelmed by dollars and square feet, this trick strips all the native units away and replaces them with a single universal metric, standard deviations.
That is exactly what it is doing. By substituting the raw, messy data point with the standardized the z-score, you transform an unpredictable infinite distribution into a standard normal curve.
Which makes it readable.
Yes. And a standard normal curve is the foundational requirement for computational training. Without that specific mathematical substitution to untangle the varying scales, the machine learning algorithm would be entirely paralyzed by the exponential complexity of the raw data.
It would just freeze up.
Literally could not learn.
That is wild. The same philosophical trick that sneaks a calculus problem past an integration table is standardizing the data that trains the digital brains of tomorrow.
It acts as a universal translator for complexity.
Which brings us to the final piece of our deep dive. We've explored the theory, and we've walked through 3 massive engineering domains.
We have covered a lot of ground.
We really have. Now we arrive at the final section of the Day 20 notes.
Yeah.
Symbolic validation. Because I'm guessing engineers at aerospace companies aren't sitting at wooden desks with literal chalkboards solving these substitutions by hand anymore.
Definitely not.
How do they actually compute this today?
No, the chalkboard era is mostly behind us. The modern engineering environment is highly computational. The source material outlines a specific operational constraint for day 20, creating a standalone, concise script optimized for immediate execution in a Jupyter Notebook cell.
Jupyter Notebook.
Mhm.
So we're talking about a living, interactive coding environment where you can mix plain text with raw executable code.
Correct. And the scripts they build does something very powerful. It sets up that exact same nested calculus problem we started with at the beginning of the theory section.
A Russian doll problem.
Right. But instead of a human manually assigning the letter U and finding the differential, the script evaluates it cleanly using symbolic integration rules. It uses a specific Python library mentioned in the notes called SIMPy.
So what does this all mean? When we talk about computers solving math, my brain immediately goes to a calculator.
Sure, most people's do.
I picture numerical estimation, like a computer just guessing fractions of a number millions of times a second until it gets close enough to a decimal point.
This raises an important question about the nature of modern computing, because that is the distinction between floating point arithmetic and symbolic math.
Okay, what's the difference?
What SIMPy does is symbolic validation. We aren't letting the machines guess or estimate. If you ask a standard calculator for 1 divided by 3, it gives you 0.3333.
Right, it estimates.
Exactly. If you ask SIMPy, it gives you the fraction 1/3. It keeps it exact. We are programming the machine to use the exact mathematical rules of substitution and reversing the chain rule to analytically prove the result.
Oh, wow. It is proving the math, not just calculating it. We've taken the manual masking trick from section 1 and we've automated it instantly.
We use these precise symbolic scripts to guarantee the math that governs the physical safety of our rockets, the stability of our electrical circuits, and the accuracy of our AI.
It's the ultimate bridge between human logic and computational power. We didn't just teach the machine how to do math, we taught the machine how to use the Trojan horse.
We encoded the elegant shortcut.
We gave it the ability to find the one string to pull.
We really did.
Incredible. If we step back and trace the journey we've been on today, it really is a single unbroken thread scaling up in complexity.
It connects everything.
We started with integration by substitution as a purely theoretical concept, right? The clever trick of reversing the chain rule.
Right.
We took that trick and we used it to untangle the marriage of velocity and time to fight the dynamic drag of a rocket.
We used it to swallow up clashing cosine waves to find pure electrical power.
Exactly. We used it to strip away the chaotic units of infinite data so a machine learning model could actually perceive the world. And finally, we saw how modern engineers use exact symbolic code to execute this trick flawlessly in the blink of an eye.
It is a perfect demonstration of how a single shift in perspective, literally changing your variable, can unlock the physical, electrical, and digital universe.
It really is.
And that really brings up a fascinating thought to take away from this material. The text shows us that the most complex nonlinear problems we face become solvable simply by finding that perfect U or Z substitution.
By finding the right disguise.
Right. But it invites you to wonder, in an era of increasingly complex computational training and orbital mechanics, as we push further into the unknown, will there always be a perfect substitution waiting to be found?
That is a big question.
Or will human engineers eventually encounter a system in the universe that is simply too tangled, too inherently complex to be simplified by a single change of variable?
That is the question, isn't it? What happens when we finally pull that one string and the knot just tightens anyway? I guess we'll have to wait and see what the engineers of tomorrow come up with. Thank you for joining us on this deep dive into the hidden math of our world. We'll catch you next time.